So I just wanted to show you. So this is the new GUI that Lily was talking about. This is not the one on Julia Hub because there's a few things that are not yet working. But you can see that we actually have a flat map, a flat brain. And if you hover over any brain region, you can see essentially the description. And then if you, let's say, want to place a block on the GUI, then you can place the icon there, and then you can make connections, something like this. And the connections are typically done with Alt or Option. It depends on, I think in Windows it's Alt, right? And then on the Mac it's Option, something like this, right? And I just wanted to show you, let me actually get my mouse. No, here it is. Okay, so everybody got this thing running? Get the, okay. Oops, no, this is the wrong one. Apps, Julia Hub. So this is the Julia Hub app, and once you're here, you can, as soon as you take the coupon, you essentially you have access to the Neuroblox application, and you can launch it. Okay, and when you connect, then it will say connecting to your application, and it will take a while because what happens in the AWS, it has to you reserve a computer and get all the resources. But while we do this, what I'm going to do is I have a little presentation to give you the GUI introduction. Here we go. Okay, so this is the Neuroblox GUI. I'm really thankful to Julia Hub because they were very generous of giving all these computational coupons. And the plan is to actually have it permanently hosted in Julia Hub. So the user interface in general, if you have icons on the screen, the way to get edges is by Alt or Option. If you click on an icon with Alt, then you get a self-interaction, right? So you get essentially an arrow that points to the same icon. And if you do Alt drag, you create an edge from one icon to the other. Left click on icon is select, left click on edge is select, and left click drag on edge anchor changes the shape so you can move around the edges. And I will show this. Okay. Then the sidebar, on the sidebar we have several tabs. One is node and edges, which when you click on a node, then it shows you the properties of the node. It shows you the parameters. You can change the parameters. The same is true for the edges. If you have edges, you can give the properties of the edges. Then we have a section on parameters, where you can create custom parameters, right? So you can essentially say, let's say I create a parameter that controls all the connections, right? So all the connections are changed the same way. There's simulation settings, parameter fitting. I don't think that parameter fitting is functional right now, so I don't think you should do any parameter fitting right now. Also, reinforcement learning, I don't think we have much experience with this particular GUI. It was working at one point, but Neuroblox is constantly evolving. And so what I wanted to do with you actually is a very simple example, and that is called the harmonic oscillator neural mass model. This is sort of a toy neural mass model. There are some works that use the harmonic oscillator, but I think actually it's a very good example for just testing out your intuition, because it's almost like a harmonic oscillator, but it's kind of a nonlinear harmonic oscillator. And you have to the challenge is to get this to oscillate. if you know differential equations, you can actually see that there's a dx dt is equal to y, and then dy dt is minus omega squared times x, omega squared times x, which means that if you take the derivative and plug it in, then you get essentially a harmonic oscillator, like differential equation, right? The solution of that would be a sine or a cosine with a frequency omega. But then you have other terms. You have essentially a damping term. So this thing alone would be a damped oscillator, would never actually oscillate properly. But then you have a connection which is an atan of the junction, and the junction could be then the input of something else. So in order to get this oscillate, you have to actually have two of the harmonic oscillators interacting with each other. So there could be a self-interaction and a interaction between the oscillators. And I will show you how to construct this system and how to get them to behave. And so the challenge for you maybe is as an intellectual challenge. So how do we change the frequency of these harmonic oscillators? Right? That would be a little test. And then the next step that we want to do is we want to build a cortical region. And we are not going to do this hierarchically, not like in the tutorial, but what I wanted to do, what I want you to do is to essentially build a cortical region where you specify essentially how many winner-takes-all circuits you use, right? And then build it and simulate it. And this is what the ultimate goal will be. You will have two cortical regions that are combined to each other or connected to each other. And you will be able to see the adjacency matrix of that coupling. So this over here essentially means the lower half is C1, where you see all the connections between neurons within a cortical region. Then you will see on the right, top right, you see all the connections of C2. And then in yellow are all the connections between, the cortical regions. And this is the flat brain GUI. And let's see whether the thing has started up here. This is now Julia Hub, okay? And so what we're going to do is we're creating a new project. And the first one is we wanted to do harmonic oscillators, right? Harmonic oscillator, right? You click OK. And then after some time, you see the canvas. So we have on the left side, we have a canvas. By the way, this is just the background. The flat brain is actually a real representation of the brain. This is just, nice looking. And then I just wanted to make you aware of all the parts of the GUI. So you have over here the sidebar with all the different tabs, right? Nodes and edges, parameters, simulation. Right? In simulation, you can, for example, say the duration, the relative tolerance, the absolute tolerance. You can specify the solver, whether it's a stiff solver or a non-stiff solver, and also the time interval. By the way, in Neuroblox, the time unit is milliseconds. Right? So 1 is 1 millisecond. We had to make this decision. And so in order to place something on the canvas, you just pick something from here, from the bottom. And where is the harmonic oscillator? So here you click on the harmonic oscillator, and then you see an icon, and then you can move the icon around, right, like this. I also would recommend that you rename this thing. So why don't we call this harmonic oscillator 1, right, like this. And then let's say we are going to take another harmonic oscillator and place it on the canvas too, and then call it HO2. Right? So now you have two harmonic oscillators. Now I told you how to create edges. Edges, you click Alt or Option. You click on the node, and then you see a self-interaction, right, like this. You can actually click on this little handle here, and then you can drag it around, right, like this. I like to have them on the side. Then you create another self-interaction on the other side. And then you can drag from one icon to the other, dragging essentially connections, and then you can move them out. Was everybody able to do this? Are you trying this? Anyway, if you don't try it now, you can try it later. You have access to Julia Hub for the whole week. Actually, until your coupon runs out. Until you spend $50 on computational resources. Okay, now what we want to do is we want to set the strength, right? So you click on the edge, right? You go to nodes and edges and you pick a weight. And I would recommend starting maybe with something like -1. Self-interaction is inhibitory. And then what you can do is you can put a weight of, I think, 5 and 6. And this is just my personal choice here. And then what you can do is, once you set the whole system up with all the connections, you can run a simulation. You click on Run Simulation over here. And then the simulation result will be over here. Now, just one of the details about Julia. Julia is a just-in-time compiled language, which means that whenever you execute something in Julia, it compiles at that time, right? Which means that because this is also running in the cloud, it will take a little while until all the differential equation.jl packages are compiled. So next time you do this, it's much faster, right? So it will take a while. So by the way, one of the interesting details about this GUI is that, and this is why we didn't even know that we can host it, is because there's actually 3 web servers that are interacting with each other. This is a very, very complicated GUI. It has a server for the graphics, and it has a server for the front end, which is Vue framework, and then it also has a Julia backend server, and they're all talking to each other. And so, for example, here what happened is that the simulation was finished, and now the data is going to send to the server that does the graphics, and now the graphics server has, returned the graphics. So this is the output. So you essentially see the 2 states that are almost on top of each other. And you can then take this graph and move it to the other side, right? You can enlarge it. You can click it from one side to the other, and then you can essentially select one of the nodes and change parameters within the nodes, right? So if you want to test whether one of the parameters, if you change the parameter a little bit, run the simulation again, and then see what happens. And now you have actually a much better oscillation, a much more stable oscillation. Okay. And your challenge will be, right, for maybe later to see if you build a model like this, how can you, let's say, double the frequency of the system, right? Okay, so what's the time? When are we ending? In 10 minutes? Okay, so now what I want to do is to actually, let's just create another project. I wanted to give you a little demo of the cortical regions. So we'll create a new project, cortical demo, right? Okay, and the demo is actually super simple, right? Because what we can do is we have a whole section of composite blocks. Composite blocks are blocks that are made from other blocks, right? And there's actually a cortical block here, and we can just put that here. And maybe we can call it C1. Okay, and here on the parameters of the node, you can see there's a number of winner-takes-alls. So you have 10 winner-take-all circuits. I would recommend to reduce that to 5 because 10 winner-takes-all takes longer to simulate. And I wouldn't actually change anything else. And just run the simulation. And this is one of the glitches, by the way, of the GUI, because it thinks that it has already there's some data in the pipeline that it thought. So sometimes you have to just click on run simulation one more time to get the new parameters. I thought we had taken care of this, but we didn't. So this is now the simulation of a cortical region, right? So you can see the initial conditions were not quite right, but then essentially after like 50 milliseconds, it established a nice. This is, by the way, the average voltage of the cortical region. And then what you can do is you can go to here to special plots, and there's a raster plot that we can do. A raster plot is essentially it picks a certain number of neurons within the. It looks at the spiking, right, of the neurons. And the stack plot gives you spiking of individual neurons. And you can actually specify how many neurons you want to look at. And then the adjacency matrix gives you the connectivity within the region. So this is random. I mean, Anand essentially created an algorithm to say, if I want a certain density of connections, then it picks random connections within the, and these are only the excitatory neurons. Okay? And let's hide this plot. Let's create another region. So if we wanted to do another cortical region over here, let's call this C2. Oh yeah, actually, you're right. Yes. So if you're here, right, let's say here, we can also look at the power spectrum. And again, it has to communicate with the graph server and come back. We'll try to get better at this. So this is now the power spectrum, and you can see the alpha band, beta band, and gamma band. Oh yeah, and the other thing is, I don't think it works. If you do the harmonic oscillator again, click on the show latex, right? LaTeX, so you can actually look at the equations of the system. You can also export data to your desktop. Okay. So let's get back to the other region, right? So let's say this is the C2 region. We may also make it small so that it's easily simulatable. And then what we're doing is we're clicking, essentially, we're going from one region to another region. Click on it and create a weight, let's say 1.5, so that we see a difference. And by the way, again, the density is a measure of how many connections will be made. Okay, and then we run simulation again. And you can play around with this. The only thing I'm warning you, if you make these regions too big, then it will take a long time to simulate. By the way, Harris, the compilation is already using graph dynamics for cortical regions internally? If you say system from graph? Oh, you have to flag it, okay. So just for your information, so I'm not using the optimized compilation, right? So the GUI is actually slower than it should be. So this is again, so these are the two regions. And if we click on any of the cortical regions, you can actually see the adjacency matrix of all three, of all two regions, and the cross correlations. I'll show a plot. Here we go. So this is, again, this is the one region, and then the connections between the regions and the other region. Okay. And that's pretty much what I wanted to show you. You can also, if you hide plot, if you wanted to be really adventurous, what you could do is, even though I think I have to give you a file for the images, but you remember that Lily showed you about category learning, right? So what we can essentially do is we can take an image stimulus block, right, and place it here, and then connect it to the visual cortex, right? And then essentially show the visual cortex images, and then that image gets then sent to the prefrontal cortex. But if you wanted to try this, then I can give you our images, and you can try this. Anyway, so that was all I wanted to show you. And again, feel free to play around with the GUI. Once we get into the tutorials, you may just want to try some of the winner-takes-all circuit, for example, in the GUI. So are there maybe questions that you have?